Good morning. Welcome to the 2020 NRRA Pavement workshops. So this year, instead of a physical in-person workshop, we'll conduct series of webinar. So today, the topic is intelligent construction technology and what we learned. So if you Google search intelligent construction technology, Google will provide the definition from the definition we posted on our website, intelligentconstruction.com. So the definition of intelligent construction technology are a combination of modern science and innovative construction technology. The application of ICT is to the life cycle of infrastructure, from survey, design, construction, operation, and maintenance and rehabilitation. It's by adapting to the changes environment and also minimizing risk. So the goal of ICT is to improve the quality of construction, save cost, and improve safety. So today we'll have 3 presentations and 2 speakers. And the first speaker is going to be slightly different from the one that posted on the website. So the first speaker, Craig from Ohio DOT, will be presenting 2 presentations on 2 topics. So Craig Landefeld is an administrator from the Office of Pavement Engineering of Ohio DOT. The first presentation will be on the asphalt density measurement with dielectric profile method. Some people call it DPS. And the second topic will be Paver mounted thermal profiling, PMTP, and some people refer it as infrared profiling. So Craig Landefeld has been with Ohio DOT for 10 years, following a successful consulting business. So Craig has served the role as an asphalt material engineer, pavement staff specialist in the Office of Construction Administration. And currently, he is the administrator for the Office of Pavement Engineering. And Craig is currently leading the effort to implement new technology to continue to develop policies to maintain pavement effectively. Craig, take it away.
All right, thanks, George. Can you hear me here? Good to go?
Yep.
All right, great. Well, as we said, there's been a slight change to the program. So we'll be talking a little bit today about the asphalt density measurement with the dielectric profile method. I'll probably refer to that a lot as RDM, or rolling density meter. That is the unit that the Ohio DOT has from GSSI. So we'll talk a little bit about that, and then we will go into some of the experiences that we've had using the thermal profiling and talk about some of those projects as well. So you can see here again, I'm Craig Landefeld with the Ohio DOT, and I thought from the start here we'd kind of go through why we have looked into some of these technologies and some of our thoughts on the usefulness of them, and then we'll talk about some of our experiences again with the rolling density meter for the density profiling and the paver mounted thermal profiling with the PMTP devices. So kind of a little bit of background as to why we started looking into these technologies. We're very concerned at the Ohio DOT, obviously, about performance of our pavements. And while distress is expected in our pavements, we see a lot of distress, some of which we have listed here, that come from built-in defects. And we see a lot of defects that show up 7, 8, maybe 10 years into a pavement's life, and You know, a lot of these defects are just contributed to age, but many of these defects that we see, if we'd have known about them at the time and prevented them from happening, we wouldn't have seen the distress in the future. You know, things like some of the potholes and some of the raveling that we see on some of our projects. We've taken a significant effort within our DOT to improve our longitudinal joints with some density measurements and utilizing some other tools like VRAM, you know, bumps and longitudinal cracking and other things. They just cause us to come up a little bit short of that finish line. And as we continually strive to improve some of these pavements, we think that a major leap forward to getting more service life out of our pavements would be to stop some of these built-in defects that we maybe don't recognize during the construction process. These things can have a huge financial impact, and if we can eliminate them, we can definitely improve our pavement's performance and long-term viability of it. So here's just some pictures. I'm sure this is similar to some other states, but just over the years, some pictures that we've taken from different projects that I've went out and looked at that have had some early failures. You know, up here we can see some longitudinal joint deterioration that was repaired on one of our pavements in Columbus on I-670. Got some other interstate pavements that we've lost some of the surface. We've seen some delamination and some potholes of the surface layer here, some very early raveling on a pavement. But as you can see, these all these pavements, the defects showed up very early, or earlier than we'd like in the pavement's life. And the majority of these, well, actually all of these pavements met our construction specifications at the time of placement. So, you know, they were paid for in full, and we didn't notice any issues with the pavements until later on in their life. Sometimes these defects that we see are pretty obvious defects. I think you can see some of the segregation, some of the texture issues and things in some of these pictures here. So, you know, these defects are very obvious, things that during construction we need to deal with and try to prevent from happening, but easily seen and nothing that would be unexpected that we might have some issues with some of the things that we see here during construction. Again, more pictures of some very obvious defects. We see some segregation. We got a rock pocket kind of here in the middle of this pavement. Over here in the far right picture, we see an area that we were looking into some density gauge testing, and we actually took a core out of the center of this pavement, and you see the guy below holding the core underneath the water. That water is actually running through that core. And this was one of our 19 millimeter intermediates. So this was a dense graded mix, not some kind of a porous mix that we would expect the water to run through like that. So obviously we got some issues on all these pictures, but again, they're pretty obvious. It's pretty easy to see them. As we move forward to this picture though, you know, the mat looks pretty good. We don't see any real visual defects here. But the question becomes, are there any? And, you know, we routinely see that we have pavements that, you know, have some issues, have some performance defects down the road that we don't see during construction. The mat looks great. Everything behind the paver looks fantastic. The cores come back in with density right where we expected, yet we fast forward 6-7 years and maybe we have some distress out there that we would cause some alarm or cause some issues for us. So as we look at the cost of some of these defects, we look at, you know, some of our 19 millimeter mixes, and this was just an example that I'd put together looking into, you know, some of the cost of repairs for the Ohio DOT. And our average repair mid-cycle of our pavements is right around 5% of the pavement area statewide. So, you know, from the time we resurface a pavement until it's ready to hit another resurfacing cycle, we repair about 5% of that area. Some of these things are changing a little bit as we've implemented more and more of the pavement management strategies, where we're hitting things with some different treatments mid-cycle, but on average we're around 5% of our repairs. So if we look at the initial cost of this 3¼ mill and fill that we put together, we came out with right around $91,000 per lane mile for the asphalt in place, not including some of the ancillary items that would have been with this project. But if we look at our typical repair costs for the area and look at a 5% repair and our average repair costs, we're looking about $12,500 roughly per lane mile, which works out to about 13.7% of the initial cost that we spent during those mid-cycle. We spent that much money repairing this pavement. Again, not including a lot of the ancillary items, but just trying to give a scale to the kind of dollars that we're spending. 13%, there's a lot of room for improvement there, and 14% of our budget for pavement cost, initial pavement cost, could definitely be some significant savings to the Ohio Department of Transportation. We also look at some of the costs of reduced pavement life. Our annual paving preservation budget would run right around $650 million statewide is what we would spend on our annual paving budget. And again, not taking into account some of the newer preventive maintenance treatments that we work on, I've worked into our pavement cycles. Right around 10 years would be just an average service life that we would get out of our pavements. Some surfaces would last longer than 10, some maybe a little less than 10, but that would be a pretty good average statewide historically where we've been. An annualized cost is about $65 million per year of service. So we're looking at these technologies that if we can prevent some of these defects, that the state of Ohio could save some substantial amounts of money to the tune of $50 to $60 million a year potentially by getting another year of service out of all of our pavements on average statewide. So now we look at, something to think about, I guess, through the rest of the project is what could you do with $65 million? When I Googled $65 million, a Gulfstream 650 came up, which is the jet here. Probably won't be buying one of those, but obviously there's several things that $65 million can buy. We look at the amount of asphalt. We could buy close to 1 million tons of asphalt in the state of Ohio. We could rehab new surfacing on probably 30 plus lane miles of interstate. Could build a new project, maybe 6 to 10 miles of new 4-lane, depending on urban versus rural interstates and the amount of work involved. So $65 million could have a very large impact on how much work we can do at the state of Ohio and our overall program. So one of the technologies that we looked at and kind of rose to the top was the rolling density meter. And we wanted to investigate some of these. We'd seen some information about using GPR for calculation of density measurements on paving projects. And so we did a small research project initially looking at GPR's viability and basically found that it seemed like a viable tool. And then we ended up purchasing the RDM unit from GSSI. Some of the benefits of the unit is it's non-destructive. We get near full coverage. We're actually measuring lines of density down the pavement. So we're interpolating between the sensors, but the amount of data increase is vast compared to coring. And also once we have the machine calibrated to the map, we can get a lot faster results. It's real-time results as we're rolling down the pavement. We're able to see density changes and potentially pick up any areas of concern and hopefully correct them before the shift would end that day. So if you look at some of our current sampling rates in the state of Ohio, our standard 446 specification requires 10 cores per day. It's how Ohio accepts our asphalt pavement with density. So 10 cores would represent roughly 2,000 tons of material. If you work that through, that's a sample rate of about 0.004%. So very small area sampled to area placed that day. This basically works out to about 10 hockey pucks per almost 4 football fields of area. And in Ohio, we measure everything by the Buckeyes. So we've got Ohio Stadium here, but a very small area. I think about 10 hockey pucks measuring almost 4 football fields. That's about 2.5 pucks per football field. As we go to the RDM unit, we're talking about a sample rate of about 14,400 samples per football field. So a drastic increase in the amount of sampling that we're seeing by using the RDM unit. So some of the just basics for how we've been operating the unit. In 2018 and 19, we did our first projects with the RDM. Our procedure then was basically we would come in and scan about 1,000-foot area of the pavement, and then once we got that 1,000-foot scan, we would go back into the unit and have it report some low, medium, and high dielectric areas that were potential core locations. Once we identified those core locations, we would scan those areas. We found that it was very important to do some roving in those areas to make sure that the density was, or that the dielectrics were relatively consistent in that area. We would find sometimes where the equipment would give us a relatively small area of a certain dielectric range, and then it would change dramatically as we move maybe a few inches away from it. So we would just disregard that area and find a new place to core. But once we had those areas scanned, we would mark them, cut cores, then the cores would be sent out for density testing. We would continue on scanning the project and wait until we got our density results back to develop our calibration curve plots and input the coefficients into the equipment to perform our data analysis. So when we start looking at the calibration scan, here's just an example of the data that the equipment provides on screen. So you can see the left, center, and right portions of the area scanned with the antennas, and then the dielectrics moving along down the pavement. And then after we have generated the correlation or generated and asked for some core locations, it gives us a table on the equipment that shows high, medium, and low dielectric regions, and gives us a station and an offset for those, so we can go back and try to find them. We go back to these areas and utilize the equipment to scan them, and then eventually cut cores for our calibration curves. So when we were doing these procedures, there are 2 methods which we could use. One was the RDM collect, core collect mode method, which scans a longitudinal line through the core area. And the other was the time mode, which allows the unit to just constantly measure dielectrics and record them, and then you can move the card if you wish, or just hold it statically right over a spot. The first couple years we've ran both methods, and each time that we have calibrated, both have given us very good correlations. It just seems as though the RDM core collect mode has always given us slightly better correlation coefficients. Not that the others have been bad, we've just gotten slightly better coefficients each time that we've used the core collect mode. So that has kind of become our standard for establishing the dielectrics for the density correlation curves. So just a little bit of background in comparison to other methods, of gauges collecting density. I looked at a project that we had done in Ohio with Dr. Sargan, measuring some nuclear density correlations with different types of gauges, and we looked at the PQI gauge and some other meters, and also found some other research from Williams in 2008 that shows some of the fit coefficients or correlation coefficients, I should say, of different non-destructive devices to measure density. So you can see the nuclear in their study, they found to have a R-squared value of 0.8173. The PQI was about 0.45. And then the PAVE tracker at the 0.3665 over there on the left. Dr. Sargan and some of our research found slightly different coefficients. We actually got the PQI meter when calibrated with cores to about a 0.59 R-squared value on our research project. And that is one of the units that we allow for some of our density acceptance under our gauge acceptance specification in Ohio. But when we looked at the correlation coefficients when we used the RDM unit, our best R-squared was right around 0.99. Honestly, we were a bit skeptical of those results. That was the first project that we did, and it was almost too good to be true. But then as we established more of them, our worst R-squared coefficient was about a 0.7 on one of our projects, and we found a couple issues with some things as we went through that project and some variability there. But our average R-squared value has been 0.88 on the 7 projects that we've scanned to date and built calibration curves with. So I guess the point of this is that the accuracy is, at least from our data, has appeared to be better than what we would see with a nuclear gauge on a typical project in Ohio. So most folks that are paving contractors that pave in Ohio utilize nuclear gauges on site, and I think they believe the results that we get from those gauges. So if you're inclined to believe the results you can get from a calibrated nuclear density gauge, you should believe the results that the RDM machine will give you, because the correlations are very comparable to better with the RDM unit. So one thing that's been really exciting to us is something that Kyle and Di and the guys at Minnesota and from GSSI had brought to us from part of our pooled fund project, was using some of the gyratory samples to build these calibration curves. And why this is so interesting to us is that, one, it doesn't require any core collection from the road, which is some destructive testing, but it's also a safety aspect for us. If we can eliminate a guy from having to go out on the road and cut cores, we can definitely improve the safety of that operation a little bit. We think we can improve the efficiency that we're getting out on the road, and this kind of testing by building these gyratory samples falls right in line with our daily quality control and quality assurance testing that's going on at the laboratory and at the plant labs anyway. The basic premise of this procedure would be that we would gyrate 3 specimens. One for Ohio, that would be a 4% air void specimen. And then we would take some material out but maintain the pill height to gyrate to higher voids to build a calibration curve. So we've only had the opportunity to test this on one project so far, and that was our Richland 71 project, where we did the bulk dielectric correlation. And you can see some of the data we've presented here. After we tested the gyratory specimens and ran the dielectric values on them and the bulk specific gravity to calculate the air voids, we found a R-squared correlation of 0.9374. So we got a really good fit on the R-squared values. We're still investigating some of the data. This is literally just came in last week, and we haven't had a ton of time to plow through it. It does appear that there may be a little bit of a shift from the data that we have here and this correlation that we've built to some of the results on site. So we're still trying to work through that and work through some of the details there, but there definitely is a positive, a strong correlation here, and we're very hopeful that as we continue to investigate this procedure that we can utilize something like this in the future to avoid having to take any cores out on the road to measure density on our projects. As you can see here, this is just kind of a general output from the equipment if you're not familiar with it. The equipment will basically allow you to set different station intervals that you can report the density. It takes several measurements and then we'll report the density in different intervals. Here we've got it set to the standard output, which is every 6 inches. You can see the 3 centers and sensors that we have here, and we've made 3 passes down the pavement covering this area. The data just comes out as a CSV. We open up in Excel. We've applied some conditional formatting with some scales here to give us a little more of a visual on the pavement area. But the data can be displayed in this kind of a spreadsheet format and then utilize some statistics on it or some other ways to evaluate it to get a handle on what you're dealing with as the data comes in. The equipment also outputs a .kml file that can be opened in Google Earth, and then some of the settings can be changed in Google Earth to change color schemes or whatever you'd like to look at. This project, we were scanning up on Hancock 68. There was actually some dirt on the pavement, and that's kind of what the red circle up here is showing, that we could actually see the drastic change in density or dielectric measurement as we went over some of that dirty pavement. And we were just kind of interested in that to see what it would do and how the equipment would react when we went over some less than ideal conditions. The pavement had been there for quite some time, and there were some issues on the project, and we decided to go up and look at that ramp and see where things were at. So, but again, nice output. Can't really do a whole lot with the KML files from a data analysis standpoint, but it does give you some nice pictures for presentations or different things. You can utilize it to make sure though that you've scanned the area that you think that you've scanned with the GPS. So some of our projects are just listed here. Not a whole lot to talk about on this slide, but these are just a list of our 2018 and 2019 efforts that we went out and scanned. The 2018 projects were relatively limited as far as number of days per project. In the 19 projects, we were able to get out and scan a significant number of days, and we'll go through some of that data here in a second. And so far for 2020, even with some of the recent issues with the pandemic, we have been able to get out and get several days of scanning in on a couple projects, and a little bit of preliminary data back on them, and we've got some other projects lined up for later this year. So we're hopeful all in all that we'll have 5 or 6 projects this year that will have several days of consecutive scanning data on to look over and compare. So this was one of our first projects, and we said we had that 0.99 R² value, and we didn't quite believe it. Seemed a little too good to be true, but this is just an example of us building a calibration curve. We had 6 cores on this project, and the dielectric values and the densities were tested and reported, and the calibration curve was then built. From that curve, then we collected the data on the project and translated it to density using that calibration curve. And you can see a histogram here of how the density data turned out from the RDM unit. Relatively normal distribution like we would expect. we had about 95% of the data over 92% density, 75 or so over 93% density. So it wasn't, it was not a, we didn't see a whole lot of issues, I guess, on the project from that standpoint, from a poor density standpoint. Obviously, we would have maybe liked to have seen the curve slightly shifted to the right a little bit and maybe tightened up a little bit too as far as density, but all in all, not a nothing too alarming here. Basically what we had expected. We moved to another project, the Franklin 71 project. Again, we went out and did the core collect mode and scanned and built a calibration curve using cores. We decided after the first couple projects to move to 9 cores to establish our calibration curves. Basic thought there was that if we ran into an issue with one of the high, medium, or low cores, that we would still be able to toss it and have a replicate, where going with just 2, we might, if we ran into an issue, we might have to go back out to do another calibration curve. But again, with this project, we saw a normal distribution. The data looked pretty good, about what we had expected, and not a whole lot of issues were found as far as poor density. So in this project, then, this is a really busy graph, so just bear with me here as we go through it. But we're trying to look at, so how's this RDM unit comparing to the cores that we're actually getting on site? And so we started plotting some of the different days of production. So we've got the lots down here on the bottom, lots 1 through 8. And the bars are representing the percent within limits. So the PWL and our range on this intermediate, including our joint cores that we would take, would be a 91.4 to a 95.9% density would get you full pay on one of our paving projects from 10 cores in Ohio. So if you look at the bar here, we went through and calculated the percent within limits using our PWL formulas for an N equal to 10 cores on this project. And for each lot, you can see the bars for the percent within limits. When we use the RDM data, we collect so much of the population that we really don't need to calculate percent within limits. We just report the amount of data that falls within these limits, because we essentially are able to capture the entire population with the data. So you can see here we're about 85, 75, 95, and we see some differences here. We also see the average core values and the average RDM values, and they can be close or they can have differences. So this kind of left us scratching our head a little bit as to what might be going on here. We're not 100% sure, but one of the things that has come up for us is that we believe maybe the N value for our number of samples when using our PWL calculation of 10, we know that's a relatively small number, and it might be too small. And when looking at these PWL calculations with that small of a sample set, we could have too large of an influence from maybe a core that landed in a certain zone density and the impact of that. So again, it was interesting data. It's a bit inconclusive as far as how well we were matching things just by looking at this data, but it was interesting to look at. Here's another project, very similar, again, a 0.88 core calibration, very similar data here. Won't go into too much of the details. Again, normal distribution, and we saw some similar trends here, maybe a little better correlation between the some of the daily trends for the averages, but again, had us still scratching our heads a little bit as far as how we were comparing overall density wise on the projects, and we'll talk a little bit about how some of the changes we've made this year to try to address and look into some of this. Again, another project, the Guernsey density data. This is from Guernsey 77, and we saw very similar trends here where trending along together, but the PWLs and the RDM percent within limits weren't exactly matching. So some of the conclusions from the RDM projects that we've had so far is that we believe that the RDM can provide some very accurate density measurements and much higher sample rates than we're getting with cores. It has the potential to change how we inspect and accept our asphalt pavements. We've been putting together some plans for looking into some pilot projects using the RDM for acceptance, and we believe it has a lot of potential for allowing us to identify some of the defects that pop up with our pavements and allow us to provide some better value for our tax dollars. We think that if we can eliminate some of these issues and utilize some of this technology, that it can provide some real-time information, and it'll allow us to improve the quality of the pavements that we're putting out there. So what's next? We're continuing to develop some standard procedures, collecting some more data, obviously. Some different mix types. We use some slag materials on some of our pavements in Ohio. We want to see how the RDM unit will react to the metal and the slag, different districts, and just comparison to our current standards. So this year what we're doing on our projects is ensuring that we are there for all of the cores, and we're actually scanning all the core areas prior to them being cut for our traditional coring acceptance. So we should have a lot more robust amount of data as far as the actual field core dielectric and density prediction versus the actual density that we got at that specific location. We're also evaluating the gyrated specimens and looking at how they perform and, excuse me, not so much how they perform, but how they compare and how we can build a calibration curve using those and to try to work out some of the details with that. We're a member of the pooled fund study looking into the equipment, and we've got some goals there of evaluating precision and bias and some effects of mixture adjustments and moistures on a few of the tasks that we're looking into. And we're real excited about it. We think that the equipment has a lot of potential, and we think we're doing well with it. We think that there's some other things that we need to iron out as far as details, but we're hopeful that pretty soon we'll be able to sell a pilot project utilizing the equipment. So kind of moving out of the RDM arena and talk a little bit more about thermal profiling. So what kind of led us here? In 2012, ODOT did a research project that I did for an in-house project where we looked into the Paver IR unit that had came out from MOBA. We purchased one. It was one of the original bars, and we mounted it onto a paver. And we went out and the contractor paved with it on 6 different projects. We collected density profiles with a gauge. So we went down the pavement in 10-foot intervals using a gauge to measure the density and develop a profile, and then we compared that with our thermal profiles. And one of our goals was to evaluate the operations from an in-dump procedure versus using some shuttle buggies and remix and transfer machines that we felt added value, but we really didn't have a great way to quantify them at that point in time. So some of the conclusions from that project, we validated the value of remixing and having some surge capacity out on the road. Thermal uniformity correlated pretty well to the density uniformity that we saw. We did find that thermal segregation did not always result in problematic density, which kind of makes sense. You can still be in the compaction window with a mixture that has some thermal segregation. But what we did find is when you have good control of your thermal segregation, that generally always translated to much better control of the density. The variability in the density was much lower when we had good control of the thermal on the project. We found that pockets of low density tended to be relatively small. That wasn't really surprising, but you know, less than 20 feet in length, and they were relatively small areas. But unfortunately, at that time, the technology just really wasn't mature enough that we thought we could go for wholesale implementation. We liked the technology, but there's really only one vendor out there at that point in time, and not a very robust dealer network. And we were just very reluctant that if we would start using this on all of our paving projects, that we would actually be able to be supported and use the equipment and implement it at that large a scale back in 2012. Here's some of the data from that project where we saw the remixing to be some of the best performers on temperature variability. We see that you know, there's a nice shift to the left of MS4 device. The remixing device tended to provide a better thermal profiles than the in-dumping did, which really wasn't surprising to us, but the data validated that. We also found that from the density perspective that we had a lot less density variability if you look at the remix and the MS4 devices. So both were kind of common sense conclusions that we felt we already knew, but the data did support that and backed it up from the project. So we fast forward 2014 through 2018, we kind of followed the research by others, and then the Veda software started to pop up, and we had seen that you know, now we've got a tool that will allow us to have some visual data display and analysis, which makes the information a lot more powerful. We also saw more vendors, some of the paver manufacturers getting into the mix as far as building equipment, and I thought we'd have a lot more dealer support. So all that started to center around a project where we were looking at implementing a new intermediate course in Ohio. We didn't have a 12.5 millimeter intermediate, and we utilized a 19 millimeter that, in my opinion, was a little bit too thin as far as the thickness that we would allow. It didn't meet some of the nominal maximum aggregate size to lift thickness ratios that you'd like to see. And we had some problems with it in the field from a segregation and laydown perspective. We thought as we start to evaluate this new intermediate, this 12.5 intermediate, and its segregation potential, that we could get back into the paver mounted thermal profilers and utilize that to evaluate some of the segregation potential on some different pilot projects. So what we did was we sold the 5 projects that you see here. And on those projects, we asked the contractor to use both a remixing device, shuttle buggy type of device, as well as in-dumping for about half of each project, so that we could evaluate the segregation potential of the material and also look at some of the data from in-dumping versus the remixing again. So what you'll see here is the Guernsey 77 project. It's not really a surprise that the transfer machine provided some better results, but as you can see here, as we look at different some of the different data, it's just as we would expect. We got some low, moderate, and severe segregation. Those are defined as less than 25, 25 to 50 degree delta, and then a delta of temperature greater than 50 for the severe, kind of the standard definition that came out of some of the research. And we see here that the transfer machine performed better, and we had more severe segregation when we in-dump. Nothing too surprising there. But on certain days, we saw some of the reverse scenario. And this is a day on August the 4th, we see where we had 97% of our profiles with the transfer machine having severe temperature differentials on the project. And this really just kind of goes to show that with any machine, you're limited by how you operate it. And if you operate a transfer machine improperly or have highly segregated mix coming from the plant, you may not be able to overcome that. And here's an example of that where the transfer machine wasn't a cure-all. It definitely had issues that day as far as the thermal profiles that it was putting out. This is another example where, again, the transfer machine actually had more severe segregation than the end dumping. This project had some issues with the edge and some cold edge issues on the project, and how they were operating the paver led to temperature differentials with the transfer machine that were actually slightly worse than we saw from some of the end dumping operations. Neither one were what we call great, but both of them obviously had some issues. So again, we learned that equipment and things are not always a cure-all. You have to still operate and do some basic fundamentals of paving in order to get good results. So this is another project that we ran, and this was actually the Vogla unit, and this was the first time that we had seen that, so it was interesting to us. But this was also one of the RDM projects that we had done. So you'll see here some of the statistics, and obviously the transfer machine performed better from a thermal standpoint than end dumping on the project. And we come over here, and again, you might remember this graph from a little earlier when we were talking about the RDM, and we look at some of the data here, and we see that the cores and the RDM averages relatively close to each other as far as how they tracked on average density. Seen some of the PWLs move around a little bit, but these were the days here, and with the gray bars were the days we were able to get out and scan with the RDM, and then the rest of the projects over here and some of the blue bars that you see. But one of the things we thought was interesting was nothing too surprising, but we found locations. Again, we asked the contractor to end dump, and we went out there and measured with the thermal data, and we looked at the data, and we can see these blue areas here of cold mix. And those blue areas are getting down in the 200 to 225 range. They have some chevrons. We can see kind of a blue line across the pavement here where it looks like the paver stopped and sat for a while before it took off again. And we can see thermally that there was a big change there. So we went into our RDM data that we had scanned, and we found the same spot and measured off of the overhead bridge on Google Earth down here. And we found, not to too much surprise, that the locations lined up exactly with the thermal locations we had over here. So these areas that we see over here on the RDM density data, some of that yellow and green is anywhere from about 89 to maybe 91% density from the RDM unit. And some of these areas are obviously substantially different than what we see in some of the red areas that are greater than 93% density on the project. So again, nothing too shocking here, just a nice visual of how thermal data and some of the density data can come together. And one of the reasons why we're really hopeful that as we move forward here in the Veda software that we can get the RDM density data in there to do some analysis and put some of these pieces together. Here again, we show some of the information, same spots here where we see that as we came down through here with the thermal data, we see these lighter green and yellow areas where we've got some thermal changes, and to no surprise, those all coincide with the paver stops where we have over here where the paver had stopped for truck changes while we were in dumping. Again, nothing too surprising here, but just another point of data that shows that utilizing the transfer devices and some of the things can have an impact when everything is used properly and having a good paving operation. So some of the conclusions, we found that this new intermediate lift thickness, it's going to fit well into our program. We can get it down, produce it at the plant, and we think that it's something we want to move forward with in the state of Ohio. From the thermal standpoint, the thermal segregation is definitely a good indicator of quality. And while it's not maybe a standalone, that there's definitely an issue at each location where you see higher degrees of thermal segregation. And when you have your thermals under control, the project definitely has better density uniformity on average, and I think we can have more confidence in what we're putting out there. We also found that transfer machines generally improve the density average, but like we said, they're not a cure-all. You can screw anything up, so just try. So we need to have some sort of measure of what we're putting down on the road. Just specifying transfer machines as we're currently doing really is not protecting us from potentially some issues. Data management analysis are still a challenge for ODOT with the thermal data, just the way our staffing and crews are set up. It's just a little difficult for us to manage the amount of data that's coming out of these things. That's something that we're going to have to look into and figure out as we move forward with all these technologies. And one of the other things is that the quality assurance and validation just kind of makes it unlikely that we would use this for a pay factor with ODOT. We think it's a great quality control tool. We'd be excited to have our contractors use it and use the information to control their operations better. But we're struggling a little bit with how we can use a pay factor and do valid quality assurance that we're required to do. Overall, we think it's very useful for process control, and some of the things that are next, we're going to have some additional demo projects and try to involve some more contractors and continue some discussion with industry on how we can move forward and utilize some of these technologies to improve. And with that, that's all I have, but Ed Morison from Shelly and Sands is going to give a little bit of some of their insights that they saw with the unit and just talk for a moment about their experience with it. So if you can all go on in, I'll bring your slide up.
All right, thanks, Craig. Yeah, I just wanted to add to what Craig commented on a few things. I appreciate him doing most of the presentation, as he has a lot more experience with several projects besides just the ones that he's analyzed with Shelly and Sands. But some of the pros that we found with using this device is information is easy to upload from the cloud and analyze using the beta software. We only have experience with a MOBA system. We did a couple of projects with the old bar system, and with the new system, we purchased that a couple of years ago, and we've done several projects with that. And like Craig said, it does highlight good paving practices, and I think everybody that's used it knows that the MTV gives the most consistent results from side to side, shows minimal segregations as long as they're using good paving practices. Definitely proves less temperature variability. It's easy to use and operate. The feet per minute and temperature readout is helpful to the paving crew on the ground because the display for the MOBA system is right there in front of the catwalk, so they can check that, and verify the feet per minute with the paver operator, and to verify a good speed for production. Cons, we've had some connectivity issues, long overpasses, paving in rural areas. That's an issue, and I think that's going to be consistent with any product that you use. RDM or the system that Craig's also using now for GPR is going to be probably another snag as well sometimes, but hopefully we get that all ironed out in the future. Wire connector damage. The portable unit is nice because you can transfer from one paver to another, but with that you have issues with guys not being careful with the Amphenol connections, twisting wires. So I recommend anybody who uses the system to buy a spare set of wires just to have on hand in case that does happen, because it's not a matter of if, but when it does happen, and it's it's not good if you're trying to get good information and then you have a connection issue and then it slows down production and causes issues there. Our paving crew all have commented, multiple crews have commented the 10-foot distance from the paver is too close. I don't know how we can correct that, but if we can, 15 feet seems to be a good recommendation by the crew, just to offset enough distance away from the catwalk so it doesn't pick up the guys walking back and forth on the catwalk and also the skis behind the paver. So that being said, that's all I have.
Thanks, Ed. I think with that, we're going to hold off on questions to the end. So we'll flip back to George and let him get on with the next presentation.
Thank you, Craig. Thank you, Ed. Excellent presentation. As Craig just mentioned, please hold off your questions till the end of Q&A sessions. Now, we're waiting for the next speaker to turn on his slide. So next speaker is Richard Hewitt from Florida DOT. And he going to switch gear and talk about their experience with the e-ticketing. So Rich has been with Florida DOT for 24 years, following a career in the residential building construction industry. He has served in role as a PE trainee, geotechnical engineer, district construction material engineer, and district bituminous engineer. He's currently the state construction pavement engineer. So Richard, take it away.
Okay, can you hear me, George?
Loud and clear.
Okay, great. Okay, as George said, I'm a pavement engineer for Florida DOT, and we wanted to provide a little bit of perspective on asphalt e-ticketing. We're also doing some concrete e-ticketing, but that's being headed up by a gentleman named John Westfall. So I'll just talk about asphalt e-ticketing today. First, I'll start out with some Florida statistics. Just to give you some perspective of our program, we have $5.2 billion construction budget for fiscal year 2020 to 2021. We use a contractor quality control system, which means we accept verified contractor testing and inspection data. We verify it at 1/4 of the contractor's frequency. And we use consultants for 100% of our verification testing and inspection work, and they handle a majority of our project administrative functions. And screen's hanging up a little. Okay, we're broken up into 7 districts, including the Turnpike. And sorry, having a little trouble here with the have 44,000, over 44,000 lane miles of on our state highway system, and 97% of those are asphalt pavement. We've got 39 asphalt contractors with 94 plants performing work for us in Florida. And in 2019, we paved over 4.4 million tons. 4 million tons a year, and 20 tons for the truck ticket. That's almost 250,000 asphalt tickets every year that we generate. And so over a period of 24 work days a year, that's almost 900 tickets every day that we're generating. That means we're helped to collect and file those tickets, to enter the ticket data into spreadsheets and compare it to another spreadsheet. That's the roadway report. To search for scan tickets and upload them to computer files for archiving purposes, and review and audit tickets. And so we started asking the question, can e-ticketing simplify, automate, or eliminate some of those tasks? What are the benefits and challenges of e-ticketing? One of the benefits is safety. Paving work can be dangerous, and we need to consider anything to decrease time in those dangerous areas. And if we can accomplish a task elsewhere or eliminate it, that's even better. And so e-ticketing doesn't require inspection personnel to be near the paving construction equipment or near traffic, whereas collecting paper tickets does. Is fleet management, and that's probably more for the contractor, but it gives them real-time truck locations, better manage cycle times, who's taking too long to get to and from the project, or who's driving too fast, or who's parked for an inordinate amount of time. And also they can use that trucking data for payroll. the truck mapping was pretty useful for folks on the project. And also knowing that the delivery of the asphalt and when that's going to occur can help the crews match the paver asphalt delivery, so you can get smoother, more segregation-free, high-quality pavement. And knowing where those trucks be when they're going to arrive allows the QC and VT to coordinate their activities. They've got a lot of inspection tasks to take care of. Go measure the milling cross slopes, and also get back further behind the rollers and measure paved cross slopes and. And also on a long shifts, they're out. They've got to eat. They've got to keep themselves hydrated in the Florida heat, and the resulting outputs from that have to be taken care of. So that knowing when the trucks will be there and when you've got a real gap in paving helps out a great deal. And the advanced materials and quantity data, look to make sure you get the right mix type coming to the job and what the tonnages are, and all that is pretty. Data is also very useful. Eliminates lost paper tickets, eliminates that paper scanning, and provides you some nice summary reports. And different e-ticketing softwares have different, pretty much the same reports, but some variations. And then that you can export the data as a file if you want to create your own spreadsheets and create your own summaries if the software doesn't have something that you want to look at. And we're hoping that provides for quicker summaries, review, and payment. Some of the challenges, connectivity is probably a big one. Poor cell service or software issues can be challenging, and as the inspectors need that real-time data to determine spread rates out in the field. Another challenge is buy-in. People are used to dealing with paper tickets, and on our 2 pilots that we did the e-ticketing on, the project personnel still collected paper tickets, and but that's been changing since our recent COVID-19 contactless ticketing requirements. And then also another challenge is that some people just have struggled with technology, using a tablet or phone for different applications. It's rare, but it does occur. And then different e-ticketing systems, we're allowing, any system to be used as long as it meets our specs. And so there's a learning curve for each system. And, you have inspector learn one system on one project, goes to another project, they've got to learn a different system. Occasionally, you might have 2 contractors paving the same project. It's pretty rare. It's usually on a very big project. They might have 2 different e-ticketing systems. And just the DOT dealing with all the different e-ticketing systems and outputs. And, but we felt like we're going to allow different e-ticketing systems because that ensures competition, and that which breeds innovation and allows the market to drive the choices, the functionality that's in the systems, and also the price, rather than just picking one and being subject to whatever they want to provide to you. And then one of the last challenges is just writing effective policies, processes, and specifications to clearly specify the contract requirements and make sure the contractors and vendors know what's required, and so the contractors can bid appropriately and we receive the proper documentation for the project, and the personnel can administer the contract effectively. And another challenge is we definitely want to incorporate e-ticketing into the inspection and documentation and payment purposes, just to really utilize that data. Otherwise, the project personnel will still collect the tickets and use them for most of the functions. Starting out with e-ticketing, we started a little bit before what I'd call our true e-ticketing venture with a system that the Florida Turnpike created, which was ticketless asphalt. And that was also tied into our road report. That first began development in 2010. They had a consultant use it just to test it out in 2012. And then we actually did some pilot projects with that system in 2016 and 2018. The first ticketless asphalt project was back in 2016, about 87,000 tons. The one was in 2018, about 52,000 tons. And we used developmental specs that were added before the contract was bid. Here's a screenshot of the inspector application for the ticketless asphalt system. And up top, you have majority of the ticket information, where what plant was produced at, what ticket number it is, when it was loaded, the mix type, the mix design number, project SIN number, and the tonnages. And then there's areas where you can enter in data, and that's the roadway report portion of it, where then you can start entering in temperatures and beginning and ending stations and widths and target thicknesses, and it'll calculate the target and actual spread rates. Much like the other e-ticketing systems, you have summary reports that have, this is a report with each of the individual tickets. You can also have summary reports that are by day and other ones by project as well. As we were doing that, we made a big push around the 2016 timeframe to go to e-construction. In our July 2016 specs, we required all correspondence and forms to be electronic. And the big, the dinosaurs were the asphalt and concrete delivery tickets. They were still paper. So in 2016, 2017 timeframe, we started looking at asphalt and concrete. So in 2017, a couple of us went out to Iowa, met with Iowa, some contract, and some reps, and Iowa showed us what they were doing with asphalt and concrete e-ticketing. We learned quite a bit, and so I just wanted to thank Iowa for that peer exchange. Over the years, we had made multiple presentations to industry, and there was some interest in the delivery ETAs and fleet management, but there's also some heartburn with the GPS on the trucks and that daily distribution of GPS units, and then connectivity was a big question mark. What happens when we can't access e-ticketing data on site? And then the bidding, what do these systems cost, and what workload to implement at the plant and project. Now, our first attempt to add, more of a standard e-ticketing software to a project. We tried to do that prior to bid. We held a pre-bid meeting, and we had immediate contractor pushback and complaints, and so it was initially removed from the contract. Our second attempt, we obtained management approval to add it to an existing project, provided we could find a willing contractor, and we spoke to some contractors and eventually added it to 2 pilot projects in Fort Myers, and the goal was just to see if we could implement one of these e-ticketing systems. A little close up there of where the project is, just out at the outer edges of Fort Myers. That was paved by Apex Paving. E-ticketing system was Fleet Watcher by Earthwave, let in 2017, and we added the e-ticketing specs by supplemental agreement to the tune of about $20,000 in 0 days. Here's a shot of an e-ticket from Fleet Watcher, and again, you've got the information of when it was loaded out, what plant it came from, and the tonnages. And with the Fleet Watcher system, you can set up these geozones around the plant and around the paver, and then as the truck left the plant and got to the paver, you had all that information on where it was. They also had a map where you could see real time where the trucks were located, and if you wanted to, you could click on a truck and get some information about the truck and what material was on it, and how many tons were on it at the very bottom there. A little bit, they had this little square here, which gave you the whole information for the project. In the center, that number 11, that was the total number of trucks committed to that project. And for source, and there was 0, which is the plant, and so there's 0 trucks at the plant. He's the destination, that's the project, and so there was one truck on site, and you can see there were 7 trucks going from the source destination, so the plant to the project, and then there was 3 trucks going from the project to the plant. So at a click of a you can quickly see what's going on in your project. And if you're overseeing a couple of projects, you can scroll through them and see what's going on, and without having phone calls and figure out where everybody is. So softwares, they have the individual ticket summaries. You can go in and click on a ticket or look at them all. And then with State Road 50 at I-95, our goals were not only implement e-ticketing, but see if we could use contractor payment, try to incorporate it into those processes and not scan tickets and just use that electronic data. And it was just outside of a town called Christmas, Florida, and right before I-95. So it was a milling resurfacing project, 29,000 tons, paid by Ranger Construction, and we used e-ticketing system called Spot On Ticketing by a company called Spot On Performance. It was let in 2018, and we added the specs by supplemental agreement to the tune of about almost $18,000, again, 0 days. Since the GPS had caused heartburn, the contractors, and then that discussion was ongoing. For the second project, we dropped the truck GPS requirement. We maintained the plant Paver GPS requirement. And so that could at least tell us where the asphalt was going on the paver. Then we added some temperature entry cells on each ticket so that we could record when we're taken by the various roadway and plant inspectors. Here's one of Spot On Performance's e-tickets. And again, it's got, information and different weights, and then areas for temperature data entry. And they had a little project dashboard where you could enter in a target tonnage. In this case, it was 250. And then as paving was going on, you had this graphic of, how many tons were loaded into trucks and how many tons were actually paved. And they had on their screen as well, so you could look at that progress again in the right-hand corner, and then the tonnages for paved and loaded on the screen, so you can kind of keep an eye on what was going on with your paving. And then each of the trucks had bar graphs for when they left the plant and they were on their way to the project, or when they were leaving the project and back to the plant. And again, they've summaries as well, different projects and multiple project summaries and individual summary to take a look at individual tickets from a listing of the whole project's tickets. So from those two pilot projects, we found that, it was possible to implement e-ticketing, and it turned out the project staff quickly learned e-ticketing systems, and the asphalt truck locations or the ETAs, depending on which project it was, helped the paving crew and the inspectors with their work. And on the second project, we eliminated the scanning of the paper tickets. And asphalt, the e-ticketing, tying that e-data into the roadway report would be the next giant step forward, is what the project personnel felt. Some of the challenges and connectivity, obtaining that real-time ticket data, and there were various causes, either your cellular service, the software, or operator inexperience. But it wasn't real common, but it did occur. And then the old habits die hard. The contractor still printed paper tickets on our two pilots, and the project staff still collected them. A little survey to see, what people thought initially, that they had concerns about data accuracy, connectivity, ability for the systems to work during paving and learning how to use it. And then afterwards, we asked if it was difficult to use. And, we had about 8 respondents, and so none of them said it was difficult to use. 7 said it wasn't difficult, and 1 didn't use the software. An office person who just kind of used some of the data that was sent to them. And then, did the vendor provide necessary training? Almost everybody answered yes. Asked if it saved time during tracking and payment. 1 yes and 6 no's. And then the benefits outweigh the time spent learning it. That was about a 5-to-3 split for yes and no, and same split for recommend using it on another project. So I think overall it was fairly positive, maybe not entirely, but most people found some value. So that was our pilot program, and then COVID-19 came into being, and we issued a DC 20-14, and that required contactless ticketing. And so that eliminated transfer and handling of paper tickets on the project site. And so we gave a couple different options. It can be direct electronic submission. So if you could connect your plant output, have that email the ticket information to the project, that would work. You could also send an electronic image of a paper document, so you could be in the plant, take a photo of it, email that. E-ticketing was an option for asphalt, and then remote review, which basically boiled down to using like a grabber tool to grab the ticket from the truck driver while maintaining social distancing, and then have somebody take a photo of that and then hand it back to them with that grabber tool. And we've got a link. We got a link in the presentation to the memo in case you're interested in looking at it. And that also has our specs for asphalt e-ticketing. When we went to contactless ticketing, since we were going from just having 2 pilots with e-ticketing, 2 pilots with ticketless asphalt, to then implementing this statewide potentially, we simplified it and took out all the GPS requirements and tried to make it just an electronic version of the paper tickets with the additional, advantages of having those summary reports and the CSV output files as it, data you could obtain. That goes ticketing. A majority of the contractors decided to use Asphalt e-ticketing, and so I think opinions are changing on e-ticketing. Initially, there was some pushback, and now people are starting to see the advantages of it. You know, better project tracking and increased oversight with less effort. And you could, you know, if you're a contractor paving multiple projects, you can look at, you know, you can have a project, several projects in just a few, you know, a minute or two. And also the fleet management aspect of it, we're seeing the advantages of that. As far as moving forward, pre-COVID-19, where the plan was to do more asphalt e-ticketing and concrete e-ticketing pilot projects. When COVID-19 kicked in, we have that memo, and e-ticketing was an option. And like I said, about 70% of the contractors chose e-ticketing, and some of the remaining 30% are evaluating that. And so we'll be in that mode for a while. And post-COVID-19, which I think we all hope will occur at some point soon, we'll rescind that contactless ticketing memo. We promised that to industry. And then at that point, we'd have to discuss the future of asphalt e-ticketing with our contractors. Should we require it and have it be in standard spec? Should we do additional pilots first, or should we do something else and scrap it all together, or some combination of all the above? And currently, moving forward, Turnpike's working with one e-ticketing vendor on direct e-ticketing data transfer to the roadway report. And you know, I'm hoping that additional e-ticketing vendors will take that same initiative, and we'll start having that data to be able to be directly entered into our roadway report from all the e-ticketing systems. And that'll require us to standardize the e-ticketing data output requirements. And we have some of that already set up for Florida DOT, but I think there's also you know, nationwide effort that would have to be undertaken to try to standardize that ticketing data output. As far as deployment recommendations, you know, just like we did, I would say try to learn from other DOTs. I know as we've gotten some experience with it, other DOTs have reached out to us, and I've spoken to probably 3 or 4 different DOTs on e-ticketing. Definitely communicate with your contractors, consultants, and DOT all the way through the process. Determine your e-ticketing needs and start simple. Try to do something basic to get everybody sort of used to it, and make it sort of simple to implement. And then after successful pilot projects are you know, finished, and then you know, just know that e-ticketing can be implemented. There's some resistance, it's likely at first, but be flexible, adjust, and adapt, and you can get it done. And keep looking to, you know, as those successful pilots move along, keep looking to leverage that e-ticketing data, you know, for quantity tracking, for payment and records retention, and make all those systems more automated as opposed to just collecting paper, and then you have to add all that up, and you know, it takes time to do all that. There's my contact information. I think we're keeping the questions till the end, but I'll leave this up on the screen for just a little bit in case you wanted to contact me outside of the meeting or outside of this presentation and talk about e-ticketing. So thank you.
Thank you, Richard. Excellent presentation. So we have about 12 minutes left. I would like Craig to start answer the question from the top down on the Q&A part. Craig? Craig, please.
Okay, trying to get unmuted there. Sorry.
Go ahead.
Okay.
Can you read out the question first?
Sure. I saw. I'll go through the questions, and I think there was a couple others in the chat, maybe, but I think they got them in the other. So, how often does ODOT complete a calibration scan? Are there site features during a large project which would require multiple calibration scan, or which multiple calibration scans would be required? To date, we have done 1 calibration scan per JMF per project. So when we would go out on site, you know, if we would start on the intermediate, as long as the JMF didn't change or there was no major changes noticed, we didn't change our calibration scan. We did try to check in with some of the cores as we went and make sure that the calibration scan as we moved through time still looked reasonable. But we weren't able to, you know, cut cores and do a full calibration daily. That's where we're very hopeful with the gyratory procedure that we're looking at, that would allow us to have some daily checks to make sure that our calibration curve is still valid as we move forward during mixed production for the project. As far as features, we really didn't see any features that would change it. It was more along the lines of JMFs or percentages in the mix in some way. So the next question was, does lift thickness play a role in the accuracy of the gyratory plugs for dielectric correlation or calibration? I think there's definitely a lift thickness on site that would start to potentially have issues with the unit's capabilities. As I understand it, the target depth is somewhere around 1.5 inches. One of the other questions, all of our projects were about 1.5 inches to up to 2 inches of lift thickness for the data that we've scanned so far. And they've ranged from 12.5 millimeter surfaces and 19 millimeter intermediates and 12.5 intermediates. As far as using the gyratory plugs, it's pretty new procedure for us. Really only had a chance to do it once, and that was last week. So still trying to work through some of that. How frequently do you need to calibrate the RDM on your projects? Again, we're kind of unsure the answer to that question. That's one of the questions we have with the pooled fund study is, what changes necessitate us having to recalibrate? So that's something we are trying to evaluate and look further into. Did ODOT look into or evaluate or observe longitudinal thermal segregation on your earlier projects? Thermal segregation with the longitudinal joint is pretty difficult, and so the answer is no. We kind of looked into that, but with the way the scanner goes to the edges of the mat and needing to chop some of that data out, that's been kind of difficult for us. Some others, Minnesota's done a lot of work with this stuff. They may have some more information on that, but we have not.
Craig, I think this is meant to be longitudinal thermal segregation instead of longitudinal joint thermal segregation.
Yes.
So it could be a cold streak along the screed.
Gotcha. Yes, we did look for some of those things. I'm sorry, I'm reading these too quickly. But yeah, we did look at and use the was it the TSI and the semi-variograms that that Minnesota has developed some of their work. We think that's important. I didn't present much on it here because I don't have a lot of data put together on it, but I do believe that that's an important thing for us to consider as we would move forward with something with the thermal information. Let's see, these are great examples of benefit. That's just a comment. It says for the Williams 6 project, with the transfer machines, just a Weiler or a remixing transfer like a shuttle buggy. Those were actually a full-size Rotec shuttle buggy was used on the Williams 6 project. Do you have any idea what would be the uncertainty in measuring density with the RDM for, say, a 95% confidence level? Our Federal Highway Division Office pavement engineer has been pretty integral in working with us on looking at the RDM technology. He actually wrote up a paper and did some analysis, I think similar to what you're asking for. I am not a statistics guy. That is not my strong point in the slightest. But Andy found that the RDM data had a 95% confidence level of 0.015% and a standard error of 0.008% density when he was looking at it. So very low errors from the statistics that Andy had run. Conversely, on 10 cores for the same data set, when he ran the standard error on 10 cores, it was about 0.48% density, and the 95% confidence level was 1.08% for the same data with the cores. Paul says, outside of Ohio, is similar RDM research taking place? I believe so. I can't speak for every state. I know there are other states who've joined the pooled fund who are interested in it and have some units and are doing some work. Minnesota is probably by far the most advanced using the technology. Is ODOT encouraging contractors to use the paver mounted thermal profiler in terms of QC? And if so, how is ODOT encouraging its use? Currently, we would allow and encourage anybody to use it. Formally, we have only been encouraging its use on some projects where we specifically put in bid items requiring it. And the requirement has just been to collect the data and turn it over to the DOT. We're hoping that with some more exposure and some of the potentials that the RDM would bring up as far as specifications, that contractors would kind of naturally be encouraged to use the device to control their operations better. But we're still having a lot of discussion with industry on how we move forward with implementing these kinds of technologies on our projects. Let's see, another question. What was the underlying decision for which you made a decision to use paver mounted thermal profiling? Was this a data-driven decision, etc.? The original reason we looked at paver mounted thermal profiling was because we're not seeing a lot of MTVs on site, and we saw a lot of truck-to-truck segregation when we end-dumped, and we were very concerned about some of the segregation and some of the issues that we might and had been experiencing because of some of those paving practices. That was the real impetus that started the look into thermal profiling. And then we used the data from those projects to then implement requiring transfer machines on a lot of our paving projects. And as we've gotten more experience with that, obviously you can still cause issues, but on average the transfer machines were providing a better end product, and we could justify it from data to pay the extra cost per ton that we were getting there. How often does your paving crew look at the paver mounted thermal profiler during production, daily, etc.? Ed may be able to talk to that a little bit better than me. I know from one project that I was pretty involved with the Vogla unit, where it was integrated into the console, the paver operator, he was looking at it constantly throughout the day and had actually made a lot of adjustments to the paver as far as auger depths and some of the feed controls to get some of the features out of the mat, which was really encouraging to me that just on his own he took some of those initiatives to adjust things and get the temperature differentials in the mat leveled out.
Yeah, I would say as far as our crews go, Craig, that they focused more on the temperature, not the temperature, the feet per minute and speed, and just to make sure the signal was still, they did, of course, look at the temperatures as well, but I concentrate on that more. And also how many stops per day. I would let them know every morning, just give them a brief summary of everything. But yeah, they were definitely interested in the information.
Thanks, Ed. Another question. How often does your paving, sorry, that's the same one. It looks like this one's for Rich. Can you elaborate on the GPS heartburn experienced by the contractors, cellular reception? If lack of cellular reception hindered transmission of the data, did you allow a daily upload?
Can I answer that? Can you hear me?
Yep.
Okay, the GPS heartburn, most of that was just the, you have with Fleet Watcher, and I'm not sure about all the other systems, but you had this GPS unit that you had to put in each of the trucks that plugged into the cigarette lighter. And the distribution and collection of all those was a big heartburn from the standpoint of, a lot of our asphalt contractors, we use second party subs who also have subs to them. So you end up with a second, third, fourth party trucking subcontracting, scheme. And so trying to collect and make sure you don't have somebody drive off without returning a GP can be a little bit of a challenge, because you might not want to necessarily have them come back to the plant, right? Off their last load, and you don't want to pay them to drive all the way back to a plant that's an hour and a half away. Maybe they can, get paid for 15 minutes or a half hour to get back to wherever they're from. And so, you got those GPS units to track and make sure you're not losing. And then there's the cellular reception. Yeah, data is uploaded as soon as it's produced at the plant, and so that data is there. While it wouldn't be ideal to do a daily upload at the end of the day if there was no way to get connection on the project, either by moving to a different area occasionally, then yeah, we would have to allow a daily upload. We didn't run into the extreme of a connectivity issue. It was more of a more intermittent, either on the project or just intermittent with the software. And so we're able to get that data. If you were in an area where you just didn't have any connectivity, then you'd probably have to just go with other contactless ticketing options of providing the data else, in another way, or doing some kind of photograph without touching the ticket. But yes, we would allow a daily upload, but it definitely creates some issues with trying to keep track of spread rates.
Craig, I think the last question is for you on RDM and also the nuclear and non-nuclear density.
Yeah, we have one here that says, going back to the density gauge comparison with the RDM and the R² values, how is the control environment between the use of the Pave Tracker PQI and the RDM? We didn't do that. As I mentioned in the presentation, the R² values that were presented, that was from Williams, a 2008 report from Williams, where they compared the 3 gauges. You could go look up that report and see how they compared those. And with the RDM, again, we didn't make the comparison between the two. Those were just our R² values from our correlation with our samples from our cores. It says all these seem to utilize electric waves to determine density. I'm just wondering if there's a possibility of electrical interference. Also, what correlations R² have you seen between nuclear and non-nuclear densities? Again, you can look at the report for the correlations between nuclear and non-nuclear. That wasn't a part of what we've been doing with the RDM project. And as far as electrical waves and electrical interference, that may be a possibility. We haven't really experienced anything that has caused us concern to date, but that would probably be a better question to ask of the equipment manufacturers, or and potentially Minnesota with some of the pooled fund activity we've done. They may have some information that could help you there. It says longitudinal segregations not only along the edge, might be the outside slack conveyors. Yes, definitely, Harold. When we were looking at that question, I was thinking about the longitudinal joint and some of the issues. On that project, we did experience some of the issues out at the edge. But certainly we've seen projects where we've got some segregation at the gearbox or at other points where maybe augers end on the screed, and all those could lead to some longitudinal segregation. And we've seen that the thermal data does a pretty good job of picking that up, and some adjustments that can be controlled. Let's see, and the last question I have here is the RDM. What is your feeling regarding which one is more reliable? The dielectric could be accurate, and the conversion to dielectric to density less accurate. Yes, very true. We believe that one of the upsides with the RDM is that we are collecting so much data that we essentially have the entire population. We think that with that amount of data, that allows us to look better for uniformity, and we really think that it's a good tool. It very much relies on that correlation, though, between density and the dielectric, and if that fails, then all bets are off as far as how good a data we've got. So I'm not sure that I can say which one is more accurate. I think that, you know, with a good calibration, that the RDM unit can give us some very good data and probably have better accuracy for the whole mat that we've put down in a day, a better representation of it than just taking 10 random cores.
All right. I guess that's the last question. So 5 minutes over, but thank you all for attending this webinar. And please give your virtual applause and big hands to all 3 speakers. And Lauren will post all the slides presentation on the NRRA website. We'll see you at the next NRRA webinar. Thank you all. Have a good day.